let's go ahead and get started with the 7th chapter of the 3rd unit, which is on future value of investments. So today we're going to calculate the future value of a periodic deposit investment, graph that future value function, and then we're going to interpret the function that we graphed. So it is a new concept, so therefore it is a new formula, but it's very similar to the formulas that we've been working with our compound interest and stuff like that. So let's go ahead and take a look at this new formula. Is B equals P to the 1 plus R over N, all to the NT minus 1, all of that divided by R over N. Now we're already familiar with all of these particular values that we are using because they're the same as they were for the other formulas, but let's go through it just in case. Our B, that is our balance at the end of the investment. P is my principal or original balance. R is rate as a decimal. N is number of times it compounds. And T is time in years. So let's take a look at the first example. The first example says Rich and Laura are both 45 years old, and they open an account at the Rhinebeck Savings Bank with the hope that they will gain enough interest by their retirement at the age of 65. They deposit $5,000 each year into an account that pays 4.5% interest, compounded annually. So what is the account balance when Rich and Laura retire? So underlining my important information here, it says that they're going to deposit $5,000. They're doing it at a rate of 0.045. It compounds annually, and they're looking at 20 years. And some of you might be asking, how did I get 20 years? Well, they want to retire at 65 years of age. Right now they are 45 years of age, so if I take the difference, that is 20 years. So let's now plug this into the formula. And we've got B equals 5,000, and then we've got 1 plus 0.045, all divided by 1, all to the 20 times 1, minus 1, all of that divided by 0.045, all divided by 1. Now when we put this into the calculator, this is going to be the really tricky part. So we got to be very careful when we do this and do it in the correct order. So I want you to watch very carefully so that you're able to repeat this process with the next you do situation. So we're going to put in our $5,000. We're going to do 2 sets of open parentheses. Notice I did that here on the problem. And then I've got 1 plus 0.045 divided by 1, close parenthesis, all to the 20th power, that minus 1, close parenthesis. And we're going to hit enter there. We're going to multiply that value by 5,000. And then we're going to now look at the lower value. And so we're going to divide that by 0.045. Let me try that again. .045 divided by 1, close my parenthesis, and I end up with $156,857.11. So we'll go ahead and write that down here. $156,857.11. So not hard, just a little bit involved, a little bit tricky in how you enter that. So it says, how much more will Rich and Laura have in their account if they decide to hold off retirement for 1 extra year? So I'm going to give you a little bit of hint on this one before I get you started. We know that the principal is still $5,000 a year. We know that they're still earning a rate of 0.045, and it still compounds annually. The only thing that's going to change in this equation is the time. Instead of retiring at 65, Rich and Laura are now going to retire at 66. So if I take that from now they're 45, I'm looking at a 21 years instead of 20. So please press pause. Try to complete this. When you're ready, press start, and we'll get back to it. All right, let's go ahead and plug this into our formula. We've got B equals 5,000 times 1 plus 0.045 divided by the 1, all to the 21st power minus 1. Got to have 2 parentheses there. And then on the bottom is the 0.045 divided by 1. Now again, the tricky part here was, could you enter it into the calculator correctly? So let's see how we did. So we're going to start with our $5,000. 2 open parentheses. It gave me 3 here, so let's start this over. 5,000, 2 open parentheses, 1 plus 0.045 divided by 1, close that parenthesis, all to the 21st power, minus 1, close that parenthesis, and enter. Now we're going to multiply it by the 5,000. And then we're going to divide it by, open parenthesis, 0.045 divided by 1. And we end up with $168,915.68. So coming back over to here, we have $168,915.68. Now the only thing is, it didn't say how much will they earn if they stay one more year. It says how much more would they earn. So they're looking at a difference, which is subtraction. So in 21 years, they would earn the $168,915.68, whereas with the 20 years, they were only going to earn $156,857.11 for a difference, or a more, of $12,058.57. So how'd you do? Okay, moving on to the second question. It says, how much interest will Rick and Laura earn over the 20-year period? So we've got the total amount, the total balance, and it's saying how much interest, so we need to subtract out the principal, what they physically put into the account, and that's what's going to give us the interest. So we know that the total balance was the $156,857.11. Now we have to figure out how much they put into the account. Well, we know, and I'll put it over here, for 20 years, they put in $5,000 for a total of $100,000. So if we subtract that $100,000 from the account balance, we see the interest was $56,857.11. All right, for this you do, please press pause, solve this, come back to me when you're ready. All right, it says, use example 1, check your understanding. How much more interest would Rich and Laura earn by retiring after 21 years? Well, we know that they earned $12,058.57 by staying that 1 year. But again, that's the total difference. We need to subtract out what they put into it themselves, that principal. And they put in another $5,000 for that extra year. So the difference, or how much more interest they would earn, would be the difference, which is $7,058.57. All right, example 3. It says, Rob and Linda open an online savings account that has an interest rate of 0.036. It's compounded monthly, and they deposit $1,200 into it. If they keep the account for 10 years, how much is going to be in the account? So, again, let's plug it into our formula. Hopefully this is becoming more familiar. We've got 1,200, 2 open parentheses, 1 plus 0.036 divided by the 12. I didn't put over here time is actually the 10 years. So it's going to be up here 10 times 12 minus 1 all to the 0.036 divided by 12. So again, here the tricky part is, can we enter this into the calculator in a proper order of operations way? So we're going to put in 1,200, 2 open parentheses, 1 plus 0.036 divided by 12, close parenthesis, all to the 120th power. I got that by multiplying 10 times 12, I got 120. Then minus 1, close that out, multiply it by my 1,200, and then we're going to divide it by, open parentheses, 0.036, divided by 12. And we get a value of $173,022.87. So we'll write that down here. We've got $173,022.87. So for the you-do, it asks the question, would opening an account at a higher interest rate for fewer years have assured Linda and Rob at least the same final balance? Well, it's kind of hard to say, but the answer here is maybe. And it really depends on how much higher was the rate and how fewer were the years. Was it 1 less year at an interest rate of 2 points higher, or were we talking 10 years earlier at only 0.5%? So it's all going to be in perspective based on what the interest rate is and how long of a time. But the answer here is maybe. Last one says that we're going to go ahead and construct a graph of the future value function that represents Rob and Linda's account. And we can do this one of 2 ways. We can plug in the value, and if you're looking at a TI-83 graphing calculator, and you go under the top where it says y equals, what we're going to do is plug in the actual formula, looking at it using x for my number of years. So I'm going to actually put this into the calculator like this, 1,200, and let me write this kind of more over to a side so I don't get in the way of my graph. So we're looking at 1,200 times 1 plus 0.036 to the 12, all to the x power, that's where it changes, divided by 1, and then the whole thing divided by 0.036 divided by 12. Once you do that, then you're going to go ahead and click graph. And hopefully your settings are correct in the window that it's showing. It should show a x minimum of 0 and an x max of, we'll say, 120. It should have a y minimum of 0 and an y max of, we'll say, $200,000. Now with that window, you'll see that at 120 months, you're looking at about 173,000. We just calculated that. So here is our graph. If we look at it, and you'll be able to trace it, if we come up on the 60 months, we're looking at about $80,000 in that 60-month or 5-year period. And that's it for this.